Hello everyone, thank you for watching this today. In this video I will walk you through our software and tell you what we did and why we did. When I first started solar, engineering was a much more detailed job, let's say. There were many people doing different stuff, like one company doing the grading, another company doing the electrical layout, another company doing the civil works, etc. And the volume was very low back then. Like you would just do one power plant in 6 months maybe, and you have huge amount of time to design everything. But eventually solar boomed, and with it the engineering requirements boomed, and people started asking like more detailed questions, like what is the analysis if this happens to be like that? What are the sources? What else we can do? What if we increase the DC? What if we decrease the AC? Like questions came over and over again, and for that reason people started requiring tools that ease their jobs. And PVX is one of those sophisticated tools that has a huge engineering background, but it is presenting you with an easy to use interface and flow. Well, as I told you, this will be a very long run, and I have my coffee ready with me, and also, just for you to understand, I have my water ready, just in case I run out of water, because it is going to be a long video where I walk through all the options of the software. So, let's go. This is the interface of PVX. It is a tool that runs in AutoCAD. It requires normal AutoCAD 3D, not the Civil 3D or not the AutoCAD LT version. The regular AutoCAD is fine for us to operate. And the flow of the software starts from all the way to the left here to the right. So we expect you to start here and do everything in order and finish here. And our software has a different approach compared to other tools on the market. The other tools on the market are called layout first software. They expect you to put the racks first, like you design the power plant first, and then you move on to doing other stuff like civil engineering. But this is not how we operate in real life. Like you don't grade the terrain based on the racks, but you make a smooth surface and then you put the racks. You cannot grade like in thin areas, but you slowly go with a bulldozer into the field and slowly trim it out, make it flat or make terraces, and then you put the racks. This is how we operate in real life. And PVX drives its power from operating real life. The first thing you do in our software is importing the terrain itself. Here we have KML import, point cloud import, TXT import, and contour line import. So KML import just imports the areas in the KML file, and then let me show you a sample. It fetches the elevations. You select it here, you select the area that you want to fetch the elevations, and then you enter its resolution. Let it be 5 meters, 10 meters, 15 meters. 10 to 5 is almost fine for a power plant. It automatically talks to our servers and gets the data ready. But this is a very rough estimate of what is available there. This is not a production grade data. This is just here for you to understand and evaluate the terrain that you have never been and you don't have any detailed information. It is just like a placeholder value that you can, play around with it. And everything you see here is in 3-dimensional form. But if you are going for a real power plant, then your options are using either point cloud or TXT if it's available, or the most used one, the contour lines. Let's try the point cloud version. here, let's first check we are in metric system. PVX support imperial and metric. So using AutoCAD standard you need to make sure that you are on the right pattern. For imperials, the right setting is 1, and for metric, the right setting is 6. But this is a very detailed thing that you can figure out later. The second part is importing the LAS file. As soon as you click the file, it reads it in the background, the file size and how many points in it. And then it asks you if you have a boundary file that you want to place on it or draw something, or you can skip this part easily. It automatically detects the EPSG code from the header of the LAS or LASet file. If it does not, it will ask you for the EPSG selector. If you don't enter the correct EPSG code, then most options that I will show you, like the civil analysis or the yield system, etc., will not work properly. So this is an important setting. Also, you can create directional slope maps here. I will show you just a minute what a directional slope map is. And you click next, and you select the grid resolution. 3 meter is perfectly fine for an LAZ file, but you can make it coarser or finer, it's all up to you. And once you click generate terrain, it reads the file, generates the terrain out of it, and presents you. So what is this? Right now we have 4 different terrains. Those 3 are informational layers. Let me do the same thing here with the KML file. Let's import the same KML again. And let's make terrain settings on. I will show you 2 views side by side so you can, sorry, that was in imperial units. I'm switching back to metric. Terrain is enabled, selecting the area. Let's give it 10, okay. Okay, right now we have 3 maps here. And the idea, why do we have them? Those are highlighting different sections of the terrain. This is the north slope. So here you have some northern slope. And the second one is south slope analysis. And those parts of the power plant has southern slopes. And this one is the east and west, so this part has east slope and this part is west slope. Those 3 terrains are not used for any data, and if we go back to our point cloud import, you will see that like the northern ones, the southern ones, and the east and west ones. So the middle is mostly flat, so there's not much going on here. But here you have very strict north areas and very strict south areas. This is an important feedback for the person designing it. Like they're in separate layers. So where are they? Direction terrain here. Somewhere in the project while designing, you might be trying to figure out if there's a northern slope there, there's a southern slope, like what was a slope, then you can instantly open that layer and get this information. It is there for you, waiting for you to use. So right now our terrain has been imported, and let's go to the next part. Let's close the directional terrain. Right now we don't need it, and move on with our sample. Let's delete this one, we don't need it. And we have the boundary. The software needs the boundary to understand where we are going to place the solar modules. So in this drawing we have our boundary. Let's come here and convert that to PV area. And instantly it becomes white. It gets the name PV1 here. So you can easily distinguish. You can have like more than one PV areas, or you can have battery storage areas inside here. I will come to those features at a later stage. So the first thing you do is you tell software where the power plant will be built. Also, we have exclusion areas, like if there are any areas that you would like to exclude from the system, you can select them here. You can convert polylines or draw polylines of your own. If you want to place roads, you can either create an area, create a polyline and convert it to a road, or you can click an already placed road and convert it to road as well. But for exclusions and roads to behave like they should, I mean, you cannot put solar modules, so the software has to know it. You have to use PVX designated options for them. Like you have to convert them to PVX exclusion areas or convert the road to PVX roads. That's how the software operates. And also, if you want, you can place trees, station, fences around the perimeter. You can even put a wind turbine, which is very popular nowadays, or you can put a high voltage line. It will draw it automatically. I mean, if you just click along the polyline and select the polyline here, it will draw it automatically. But let's roll back to what I said, being terrain first. What does it mean? Before going to the layout part, which is here, we have two areas that we have to handle carefully. The first one is the civil analysis part, where we understand what this terrain is all about. And the second one is the grading part, is how we grade the terrain. And then we move to build layout. We don't do the opposite, like we build the layout and we start grading. We grade first and then we build. So let's move with the civil analysis and the soil compaction here. This is a very unique feature of PVX. Right now, in this feature, we basically query different satellites for different values. And using those values, we map those values to the hardness of the soil. Sorry. Using this hardness, you can assess like what is the driving power, what is the pull-out resistance. So let's click our boundary, and now it is talking to our servers and getting the values mapped onto this area. Almost done, and yes, here. Now let's close the terrain here and see everything. Okay, now this is our map. It has some greenish areas, light greenish areas, and yellowish. But what do they mean? Like, what is the idea here? Okay, let's focus on our legend. We have soil classification coming from very soft to very hard. And this means something here. In an ideal power plant, we want to be around here, like from medium firm to hard is where we want to be. And from what this file has, like we are in a good place to install a power plant. So we have two things, like can we drive the piles? And if we drive the piles somehow, then what will be the pull-out resistance? We want to drive them easily or with medium hardness, and then we don't want them to come out, so they can tolerate wind power or snow, anything. What we understand from this part here is, if it is the very hard part, like if the terrain is here, we have to do pre-drilling. Like pre-drill, create a hole in the soil, then put the pile inside, put some gravel and then concrete and make it structured, because the pile itself cannot be driven inside. Or if it is soft to very soft, think it like sand, like near seaside. You can easily drive it and it will just come out easily. So for such soil, you need to use concrete blocks at the bottom of the piles. So this edge here and this edge here tells you that the capex of your software will increase and you have to plan for additional concrete or drilling, or additional costs are coming. But if you are from here, you are mostly safe from what those edges offer. This is not a very final inspection. You always have to do the ground inspection before you start the power plant, but it provides you, in addition to this, a little bit more info. In some cases, there are areas that moves from soft to medium to hard, and in those transition areas, while you do pull-out tests, you mark them using this data, and you do more pull-out tests on those transition areas. As a result, if there are like hard surfaces and normal surfaces, you can use high capex items on the hard surfaces and low capex piles on the normal surfaces, and you can map out exactly how the transition goes. So your capex will be much lower and your project will be much more stable, because before going to the field, you know how it is going to operate. The resolution for geeky people that are currently thinking in their mind like, what is the resolution of this data? It is more or less 15 to 20 meters, something like this. So expect a swap of like 20 meters while mapping the area. But as I told you, like, this is not the final information. This is a complementary information while you are designing your power plant. So know this before moving to the next section. The next part is about hydrology. Let me close here, soil type, and let's get back to the hydrology analysis. This is also a very important feature of PVX that you should be using in your project. This analysis does not take into the last 50 years of precipitation and try to mean it. It just takes the elevation into the meaning. So this feature tells you if it rains, the water will go like this. So let me close all those layers first and show you the basics. Okay, now this is our area, totally unknown. And we first open the draining system. If you look at it, you will see that we have some white lines coming here, colliding here, and some straight lines here. So let's open the terrain also. And if you check it, like, you will see that there is a path here that goes like this, and another path here that goes like this, and also some flat areas. So here, if you look at it in three-dimensional form, let me open it like this to grasp it easily. As you can see, we have a terrace-like structure here, and the water is coming in this direction, and another subcatchment, a valley-like structure here, and exiting here. Let's open the pour points, like where this water will go. Aha. So right now, as you can see, those water will be ejecting from those points and those areas from those points. And if you look at here, you see that many straight lines. Basically, what it tells us that like this area is flat and the water will slide over the surface. It is not a very harsh path, but it will just slide over the surface. So what makes this data useful? Like how we should be using it? Again, the most important part is we give you, if there is any subcatchments here, Okay, here we have a subcatchment area, like the water will collect in this area and eject through those areas. And if we draw the unavailable areas, we put red markings. What this tells us that here we have a pooling area. The water will collect here from those areas and will eject through here. Don't put any transformer here. Like if you have any critical infrastructure, don't put it here. Like simple as that. If you have to put it here, then you have to think in detail about how you will drain this water, because you don't want your transformer to be flooded when it rains. You don't want it. And you know what? Using this technology, you can evaluate this information without starting the drawing, without starting the power plant design. Like we know the civil analysis right now, we know the terrain, and we can move forward with this information at hand. Also, we have a suitability layer, but it is exactly the opposite of the red area, so not much more of an information, it is just an informational layer. So this part proves a very useful information for your power plant. Now, what we know about it is that this surface is normal, like you can drive at a normal pace, and we expect it to hold with a nice pull-out resistance. Also, we know how the water will behave, so we will exclude areas that the water will eject, and we will not put any transformers there. Let's move on to the second part, the grading. Okay, all the people using similar software up until now always thought about adjusting piles or adjusting terrain to the piles. This was your grading approach. But it does not really translate to what happens on the field. What happens on the field is a different beast. Okay, so let's take this iPhone and think it as a rack. Like let's say this is a fixed rack system with its slope and everything. In some cases, those racks have like 10 different piles, or you can make the same rack with 6 piles. This rack can have some crosses at the back and the front piles, or it might not have any crosses in those piles. If you put more steel, more crosses, your price per rack, let's say, increases to $200. But if you use a very lightweight rack with less piles and no crosses at the back and front piles, then you end up with a $100 rack. So, but they all have the same amount of solar modules on top of them. So what is the difference? The difference is their ability to handle the slope. On a $200 rack, you can handle slopes of, let's say, 20%, like this. But on a cheaper rack with less metal, you can maybe handle 5 to 10%. And this little detail affects how you grade it, because you can make a flat, like I can here in this drawing, I can make the whole land flat, so any rack with proper snow handling will hold. Or I can use the least amount of cut and fill and use a slightly more expensive rack and get a much more optimized design. This is where the core engineering part of this software gets into the play. So we have the north-south threshold slope and east-west threshold slope, because construction manufacturers have different limitations. Like they can have like 15 degrees east-west slope limitation and 5 degrees north-south slope limitation. So before you go any further with your design, learn what your rack manufacturer provides, like what are their limits. So here, let's say 20% east, west, and 20% north, south. The first thing I do is I select the area. My second option is slope transitions, like what will happen at the boundaries, like this white area, the boundary, what will happen here? If you make it soft, like it will grade slowly, but it can at some cases go outside the boundary, but it will give you a soft slope. If it is a very hard boundary that you don't want to pass and you want to reach the target slope here, then you can select hard slope and it will just cut or make it like a 3-meter wall at the boundaries. It is based on your specification. However, the most important feature is here, like how should we do the grading part? We have two options for you. The first one is the cut and fill ratio, and there's a slider here. So if you leave it in the middle, the software will try to cut and fill equally. This translates into not moving soil from the project area to somewhere else, because if you keep everything in the project area, your average price for cubic meters is maybe $4 to $5. But if you ship it to somewhere or bring soil from outside, then your cost can go up to like, I don't know, $15, maybe $20 per cubic meter. So this is a huge cost slider actually. So for most projects, people leave it at the zero, but in some cases you just want to cut more, then you can slide it here, or in some cases you want to fill more and you slide it here. This directly affects the performance of the algorithm. So if you slide it to cut or fill sections, it will take longer to complete, but in the middle the algorithm runs at its fastest. And we have another option, which is the maximum fill height. This is one of the important obstacles that we come across in projects, especially in Europe. Europe is very strict about what goes up and down in the soil. So here we enter the maximum fill height. We basically tell the software that everything above that slope, clean it. Like make it flat, just like a bulldozer goes to the field, start moving. If you reach an area and you start filling, and at any point you reach a fill height of 1 meter, stop. You cannot fill it anymore. So whatever you do it by cutting. So cut more so you don't fill more. This is useful in some different cases. Most people use cut and fill ratio, but know that our fill limitation is available for you to use. And let's apply it. Right now the software is going over the terrain, finding the points that are above our threshold, and it will apply smoothing to those areas. And as you can see right now, we have a new terrain. Let's zoom into this section. So this was how it was before. Like we have a high slope area, and this is what became of it. Right now we have a much smooth area, but no, let me show to you this in 3-dimensional form. Now it is much more easier to use. I don't like 3-dimensional form. It is always slow and it's always a pain, but it gives you an idea. Like this is the terrain after, and this is how it was before. So we made slight adjustments in the areas, and we made it ready for rack placement. As you can see, we did not touch any place, any point that is below our threshold. So the idea is we grade it like we do in the field with a bulldozer in the least cut and fill way. Okay, so let's get back to the normal view. So anyone asking for this table? So here we have our cut and fill analysis, and it basically tells us like what was it before what is it after, and what is the cut, and what is the fill ratio. As you can see, our numbers are very close. So this is what this algorithm provides us with. This is an information available here, so you want to print it out, but always you can go to here and get the plant information. Sorry, no X here. You can get the cubic breakdown here, and it will cleanly display it once more. Sorry. Yeah, it basically generated the same thing again here. So let's move on. Let's talk about what we have done with the terrain. So here we have the cut and fill section. It's another layer. I open it and it tells me exactly which parts of the power plant it did cut, the red ones, and which parts of the power plant it did fill. If you zoom in, okay, now this is one point here. This is the previous value and this is the current value, and exactly at this point we cut 4.4 meters. And if we combine the cut of those 4 points, here we have like 471 cubic meters of cut exactly in this area. And if we go to the greenish areas here, now this was what it was before. Now we added roughly 1 meter here. So here exactly in this point we have a fill of 1 meter. And if you combine those 4 points, you end up with 76 cubic meter of fill here. So this is what we mean by constructability. Our software has been tailored for constructability and avoiding rework. We want you to have all the information to design a power plant. And when this project is shipped to the ground, I don't want anyone there to come back with a new information telling that the project you created cannot be applicable. This is not something we want. We want you to work easily, and whatever you receive, it should be done. Like, it should be easily built. So constructability is our first and foremost promise. And the second one is avoiding rework. Whatever you do, whatever you want to change, we don't want you to go all the way back. You can just keep the work and rotate and mutate it in the ways that you prefer. So if there's a change order, don't stay awake until the next morning. Like, open our software, do your work easily. So save your time. This is what this software is for. And right now, moving on, let's go to the layout finally. Okay, it's been 33 minutes since I have been talking, and we haven't done any solar layout yet. I don't know if you have noticed, but we are still in the terrain phase. We first imported it, did some areas, exclusions, civil analysis, grading, and now we have everything we need to go for a great design phase. So we click the build layout section and this nice little window pops out. And here we have the create fixed and create tracker sections. If you click create tracker, you have the single row, multi-row and TFT options here. And if you click create fixed, I mean, it is the regular fixed system and you have the option to make it an east-west zone. The first thing you do is you select a module. Let's select a fancy one. Now the module is ready and you have a nice, beautiful 3D visualization of the power rack. We have two modes here. There are people that just want to be done with the design and they want the sensible defaults. I am one of those guys. And there are people, especially rack manufacturer, well, that's their nature, extremely detailed about how they design it. So, for people like me, you just select a module, you just give them a name, that's it, let's name it after my name. I always use the configuration like 2x13, for example. And what is the orientation of the solar module? What is the angle? Like I said, 13, let's make it 13. And 2 rows. And I'm done with it. Like, I'm really happy with this design. It is perfectly sensible. As you can see, the pile count changed, pile distance changed, everything looks nice. For me, this part is perfectly fine. But if you are one of those people that want to go the extra mile, okay, here is your game. You can simply enable the auto mode, and then you can change the pile count. Let's make it 8. Now you have more piles. Let's make it 20. Now you have even more piles than you would all anyway require. And you can, let's make them 2. Not enough? 3. Maybe slightly better. All the details you need, like the overhanges, distance to float pile, underground depth, or east-west, anything you need is here. You can play around. For the sake of simplicity, I always move with the manual part. Sorry, automatic part. But we have the designed racks here already, so I'm not going to create anything new. I have a smaller rack and I have a large rack. And during the design, you can use 2 or more racks to place around. Basically, it tries to put the longest rack first, and then if it cannot put longest racks at the boundaries or areas that doesn't fit, it sprinkles short ones. Because most of the time, the longer racks are cost efficient, so we are prioritizing them in our software. And now we selected 2, and here we have 4 options, and they serve different purposes. Left to right and right to left basically aligns the racks in the leftmost and the rightmost direction. The reason we have such feature is, like, if you want to cramp all the megawatt that is installable into that area, then select one of them. There will be no roads, nothing, like it will be just solar modules. And also we have the centric grid, which is the default selection in our software. And centric grid is the one that draws beautiful roads, aligns racks to each other in the drawing, places everything beautifully, and you get that nice, good looking solar power plant design automatically. It is the option for you. And we also have the draw alignment feature, which is something we implemented for people that are coming from another software, because some software has a thing called draw alignment. I mean, why would you draw an alignment? That's a whole different case, but some of our users ask for it, and here it is. If you click draw alignment and you draw a line, then it will align the racks to that thing. But I'm not going to use it here. So the third thing we do is we select the PV area. We tell the software where we will place it. You can have more than one. It is for you to play on. So one of the most important features is the terrain slope checking. We have been working with the terrain, but sometimes you don't want the grade. You just want to check that if this terrain fits to your specifications. It is this option. Like here, we tell the software that, look, we have a 3-dimensional terrain. We have graded it. It is great. I mean, you can move forward with it, but just check. Like if any slope for any rack goes 25% in north, 25% in south or east-west direction, 25% east-west, don't put any rack there. Anything above those limits shouldn't be in the drawing. Okay. Also, we have the dynamic pitch option. Since we know where this project is, like we have set the coordinates and we know the latitude of the project. And if you know the latitude of the project, you know the sun's angle for throughout the year, for 8,760 hours of the year, we know where the sun will be. So based on this value, we can calculate the pitch distance according to the terrain. It is a little bit complicated feature, and if you use it, you will get rows that are not perfectly aligned, like the distance between each row, let me show it to you like this, will be different, like short, long. But it will help you to have a shading effect uniformly all around the plant. So expect to have roughly 1 to 1.5% more yield throughout the year, but you can install slightly less capacity. So there is a trade-off. This is the core engineering part that you need to optimize. Sometimes you can use it, sometimes you don't use it. If you don't know what you are doing and if you want to stick to the normals, then don't use it. So get a perfectly aligned drawing, because even though this is a technical thing, people that look at the designs and say they don't look aligned, and then you spend your 1 hour telling them about the dynamic pitch distancing, the shadows and everything. So if the client doesn't care and if you don't want to go into too much detail, just turn it off. Friendly advice. And the next part, if you enable it, now this is closed, and if you disable it, now they are enabled. So here we set the distance manually. The system, based on your rack selection, creates a distance automatically, but you can always play around those values to compact more racks or less racks. Here we have the corridors. While placing them, you may want to have some roads, like vertical roads, horizontal roads, roads with different gaps. Like I want my vertical roads to be 10 meter, the horizontal ones to be 5 meter, and I want one row after each 15 rows and one row after each 15 columns, etc. So you will have roads like this. You can enable them here. If you close it, the whole area will be filled with racks. And this is the boundary road. Think it like an offset distance, because people ask me like, can we offset 5 meters from the boundary? Yes, you can. Yes, you can. But technically, even though you offset, the area you offset it is used as a road for you to reach those points. So we don't have a specific feature called offset, but we just designate them as road, and you can change the width of the road here to however you please. And once you are done with those settings, you click build, and it starts building the power plant. First the roads and then the solar modules. And when I see this view, I really like it. The colors, the blending, the beauty of a new power plant being born. Like, I'm simply in love with this. And if you zoom in, you will see that we have very simple polylines, like just a rack and nothing more. And we have the slope of each rack. And if it is more than 10 in any direction, it makes it red. Just to give you a sense of it. So, are we really drawing basic polylines? No. We have all the data you need inside the system here, but we don't show it to you. Why? This software can handle roughly 1.5 gigawatts of power plant in one DVG file. In the background, we have such optimizations that, like, we have went to very extreme ends to reach those optimizations. this is one of the features that we have to add to software. So this data is hidden. If you enable that layer, you will see that each solar module and pile points and everything is built in there, but they are behind a layer called racks, and that layer is always frozen. Because if you don't freeze it, if you are working with a 1 gigawatt power plant, if you open that layer, your AutoCAD will certainly crash. There is not much enough of memory to handle this amount of thing. So we keep our objects simple and we show you the data you need when necessary. Just like this. Just the boundaries, we call them BB, boundary box of the racks and their inclination and the roads. Right now, our design is like we placed racks, but we want to see something more about their inclination on the terrain or the shading effects. Here we have the tools section. We have the move racks, like if you want to move a rack around, you can click this one. I will come to design wizard later. We also have shading analysis, like if you want to see the shading at 5 p.m. Let's run for it. And here, this is how the shading looks. Now all those racks have some sort of shading in them. You can play around, you can see how this shading is behaving. It's totally, again, your call. Let's close shading layers because I don't want to stay slow. Okay, now back to design. And we also have a tool for rack slope analysis. Let's say I want to highlight the racks based on their slopes. Let's apply it and see how our racks are situated. So here they're almost flat, but in this area my slopes are higher. And you know what? I am not really satisfied about this area. Let's say I want to make it flatter. Okay. I want to apply a general grading that will blend to its surroundings and will handle the racks and its complexity. Let's draw a polyline here. Start here. I'm just doing an arbitrary polyline, nothing serious. Just to show you. Okay, here and one here, and then let's close it. And I want to convert it to an area that our app can work. And now I go back to grading, and here I select the area. And then I want to make the threshold here, let's say 10. Let's apply grading. Okay, the terrain has been graded. The racks have been removed, replaced, re-rotated. And now we have new system. But have a look at this, like our boundary crossed those areas. So right now, those racks, those two racks, and those racks are in a very high slope. So if you do it next time, like select it properly, because right now, while the racks inside are now perfectly smooth, the racks at the boundary are suffering from high slopes. That is the normal outcome. So The idea here is you can apply grading before the design or after the design, because this grading is what a bulldozer does. Like it goes there, goes over and over again, gives you a bright surface, like a flat surface, in the least cut and fill possible. There are people asking, I know, about their grading from other software, which we call adapt terrain to pile. We have this feature in our software just in case you want to fall back. It's here. You set the height for the front or the back pile or the total pile length, etc. And then based on this information, it checks the length of each pile and moves the terrain beneath it. This procedure applies to flat areas. Like if you are, let's say, in Netherlands and you are doing a power plant on an almost flat surface with some bumps ahead, then this type of Earthworks may work. Like it generates a smoother area and it gives you a usable area for racks. But if you are working on mountains, on very high surfaces, this generates zigzags like this. Like each rack has their flat surface and the next rack just falls down and you have a huge slope. And the end solution you end up with is not really applicable. Is it correct? Yes. The calculation, the cut and fill, are they correct? They're perfectly correct. But you cannot apply that design to a field where you need to cut or fill huge amount of mountains. And for very harsh terrain, the gradings, the cut and fill analysis we provide is the way to go. It is something buildable. Because eventually you want to ship this information to the field and you need the right information for it. Let's fall back. Let's get the leveling back. Yeah. And let me remove it. Because here we have an export for Earthworks. This is the document you ship to your contractor here. And we have the northing and the easting, natural ground level, final ground level, and difference. So for each coordinate, you can see the data here and you can ship it to your contractor. Simple as that. Okay, so let's move on. What else do we have? Let's Now again we have our beautiful racks, and for this part I would like to highlight that you can also do capacity iteration. Like you can scan the terrain here and you enter the parameters and everything. The software iterates for you, and based on the row spacing it tells you how many megawatts, how many racks and modules you can use. And if you just select one and generate the layout, it automatically generates it in the background, in the drawing, and you can move forward with it. Or if you want to understand like how this terrain is flowing, like what is the cross sections, you can take it like this, here to all the way to, say, here, cross. And here it shows you beautifully how the racks are aligned. The white line and the white line is the current terrain after grading. The purple line is its previous version, so you can see the old terrain, new terrain, and how the racks are placed on top of them. Again, all the terrain information you need is ready for you to play around. And one important feature that I would like to show you is the import layout and import PVcase design. So in the import layout, basically if you have a design that you have designed manually with racks and etc. placed, you can generate the same racks in our system, and you can click import layout function and select them, and it will automatically convert them to PVX objects. Or if you have a PVcase design that you have been doing previously and you want to continue your work here, you can click the PVcase design import function, and it will automatically convert the tables that you have there into our own tables. So you don't need to manually go back and forth to convert them. The software does the conversion for you automatically. Well, with the layout part, we are almost done and we can move to the electrical design section. Our electrical design section has been designed for simplicity. I have seen many tools on the market that gives you all the details about how you should be designing it. Like you create trenches and then you give it a name like AC trench, and then you assign that AC trench from string inverter to the transformer, and then you create another DC trench this time, and this time you assign a DC trench with the strings and the inverter again, or the DC combiner box, and then you route the cables through those trenches. It is a huge complexity, and we don't need that much complexity in 2026. Like, we have the technology. What we usually do is, like, we place the inverters or combiner boxes in vertical rows most of the time, and we route the string cables to the nearest combiner boxes or string inverters, and then we route to the main central inverters or the transformers and so on. And we don't need to do it by hand, or we shouldn't be aligning an inverter to an alignment line, or we shouldn't be aligning something to another something alignment line. Do we have those features? Yes, we do. We have the trenches. You can generate trench, assign, draw a polyline and make this polyline a trench, and then route cables, and then assign strings, and then put devices, remove devices, like everything we have. But should we be using it? No. We have simpler options. Like, we are here to save your time. We are here to help you do things in a much more efficient way. The first thing we do, we have a flow here, like 1, 2, and the rest will open the more I click. And we will have a nice flow here that does all this complexity for you. The first thing is we create a preset. So right now we have 2 racks. One of them is a long rack with 26 modules in one area and another 26 here. So it has 2 strings. You can make them like U string, you can make them leapfrog, single row, whatever it is. Let's make them single row, and I'm saving this preset. And we have a smaller rack because we placed a smaller rack, and I want them to be a U string because it is just 1 string. And right now I saved my strings. Now the software knows the long racks have 2 line strings and the short racks have 1 short string. I can do custom stringing as well, like combine 2 racks into 1, or combine 2 left and right racks into 1 string. You can create them using the custom option. The order of application matters. Like, if you just apply the long strings, let's say you apply the long strings here, all the long strings that it can find, it already handles the stringing. So if you have a combining string, it won't work. So if you have some sort of like up, down or left, right combination strings, you have to do them first before doing the single tables. And then let's do it for the remaining smaller racks. And all my stringing is done. Right now I have 3107 strings. And our stringing section is complete. All the racks we have has their stringing ready. And the next part is selecting the PV area and going for the design. Okay, let's get you back to days of PVsyst. PVsyst is the first software back in 2008, I think I used, and I had no idea what it was doing, and I was trying to get a report out of it. So it is the same logic here, like you select the inverter. This is the main part you do, and the second one is how many inverters per transformer you want to use. Let's say 16. Okay. What we know here? We know that this inverter has 24 string inputs. Okay. But in our field we have 3107 strings. So in order to assign all of those strings, the system automatically creates the inverter count. So it says using this much of inverters, you can connect all the strings. But I have a DC-DC target ratio. Then how does it operate? In PVsyst, most of the time we increase because the DC-AC ratio label and the series and parallel selectors are on top of each other. So most of the time, once the inverter is set, you play around with the DC, and we call it DC overloading because we have the AC and we overload the DC to see where it is leading. But this is not a yield tool, this is a design tool, and we first graded the terrain, placed the racks. So what we are certain of it is we have the DC ready, like we cannot change the DC anymore. So by using the DC AC as a DC overload in our software, it is technically AC underload. So it's a different concept, like exactly the opposite of what we do. And here I say to underload like 1.3%. And the software tells me, look, you have 51 megawatts of racks here. And if you were to apply this, you should need this amount of inverter AC power, but you have strings, and in order to accommodate for all strings, and if you are not going for the Y connectors, then this is what you get, like you have 130 inverters planned. Okay, this is the first thing it does, but it also tries to divide them equally. So if I target like 16 inverters per transformer, we have like 4.8 MVA of transformers, 8 of them, and then a very small transformer. So this doesn't look very nice. I wanna increase the power a little bit. Right now I have a 5 MVA transformer that I'm pretty much hitting the limits, and I have one smaller transformer here. So my design is covered. Right now the software knows I need to place 8 transformers in the field. Look, this is the part that people go ahead and do stuff manually, like you select the strings and then you assign them to a transformer. And if you want to do some changes, this is the avoiding rework part. If you want to do some changes, then you have to like unassign a string and leave that inverter empty, or put something else, or bring inverter from somewhere else. There is a huge amount of manual things that people do. We don't want to do it. We just want to get our string count assigned properly to the inverters. Like we know the string count, now we know the inverter count, and we know the transformer count. And we want to apply this to the drawing. This is how it operates. So I am applying coloring for the transformers. Click Save. Now the design itself is saved. Our electrical design that we remember from PVsyst days is saved into our memory, but it hasn't been placed in the drawing yet. So here we have 3 green ticks like stringing done, scope selected, configuration done, and now we have the place devices. And this is the tricky part. We have the auto mode and the manual mode. The manual mode is the painful mode that we have been talking, like you assign DC trench, assign AC trench, generate cabling, generate selection, like all the busy thing like you see here and here is in the manual section, but we don't use it. No need anymore. We just select the auto and we click place devices. And the software knows where your strings are. That's a very useful information. Because we want to achieve the least amount of cable length, because we are optimizing for the least amount of voltage drop, hence the cable losses. So let's cluster the transformers and then find the centroid of those areas, and let's place the transformers at those areas. Like, pretty straightforward, isn't it? Think of a circle. The only point that is the shortest distance to every point in the circle is the center. So we want to put the transformers into center of the area. So the software does this calculation in the background, and it asks you like, look, I looked for it, I calculated, and those areas are the ones that we should be putting the transformers. Are you okay with this? There might be some cases where it is not really central because it always puts the transformers into the roads. Like, you cannot put the transformer that is not a road. So keep this in mind. And I either manually pick them, like you want to play around with some of them, you can manually pick them, or you can click approve. And right now it is placing the transformers in the background and placing the racks, assigning the racks to their transformer. As you can see, it placed everything. However, it said like, since I removed some of the racks, our last transformer will have some less. So can I rescale this transformer? I say rescale, and it handles the last one and do all the labeling of the power plant instantly, and routes all the cables and gives you the design ready. So right now we have the labels, we have the transformer, we have the devices placed on vertical roads. Strings are going to the inverters, and then inverters going back to the transformers, and they are all color coded. So the transformers, the inverters, the cables and everything is done. Like, the design is done. If you want to switch something, like if you want to move a device from here to here, we have a nice beautiful move device button. We don't want you to unassign something, then add something, then reassign something, and then reroute the cable. Like, this is done. We want you to pick the device and move it around. It asks you like, should I generate the cabling again? Yes, please. And there you have it. The cabling has been regenerated. You don't need to do anything. Your design is done. Just ship it. And I think in 2026, this is how you should be designing. You want to move the transformer. Just select the move device, click on the transformer, and move it around. All the cables of the transformer will handle this complexity. And let's regenerate it. And there you have it. The cables have been regenerated. Place it anywhere, and it will regenerate all the cables, and you will be done with the design. This software is not perfect. Like, it cannot do it everything like a human would do, and it will just obey the algorithms and the technology we have, and it will try to do its best. But it will do it much faster compared to a human. And after you get this initial view, you can just play around with it and make it your optimized solution, because it applies the rules correctly. If you set the rules, it applies the rules correctly. And now we have the electrical design ready. You can click generate SLD button here. It asks you like, should I aggregate it or do you want to see everything in full detail? Let's click full detail. And meanwhile I drink some water. And you have your strings connected to their protective equipment, connected to the inverter, their ratings. Those ratings are calculated based on the inverter information, the module information, because remember, while designing the racks, we selected actual solar modules. And inside those solar modules, we have all the data, their power, their width, their sensitivity to temperature, everything, all those data. I mean, if you are again using PVsyst has PAN files and OND files. You can import them here in the product section. You can import them, and it has all this data. And if you have all the solar module data and all the inverter data and all the distance data and the cabling data, then it is just mathematical applications that you have to do and place the protection equipment. They are placed based on the IEC settings. So you see all of them here. And let's get back to the model. And nice, we have a great power plant and we want to do some battery storage. And how does it work? Okay, our approach to batteries are different. But how different? What is the difference? When you see the tools online, it is always about how many batteries you put, what is the power that gets in, what is the power that gets out, etc. But our approach is, remember, it was always constructability, and constructability starts with security. Like, how secure are we designing? Are we really compliant? Are we really compliant? Do we have any people, any building or anything around us? So our system takes this compliance to a new level, and here we have the settings. So we have a rule engine. We have IFC rules for fire, we have NFPA rules, or manufacturer clearances only, whichever you prefer. So you select the rule set, and then you select it to be AC coupled or DC coupled. What is the capacity target? And here it automatically sets the settings, like what should be the exposure setback, what should be the difference between the groups, what is the power limitation. All according to the rules and their own section has been implemented into our BESS engine. So we want you to design the best possible, but we want you to design it securely. This is what really matters. Designing something that lasts long and obeys the local regulation is the way forward. It is not just fancy blocks, but it's a whole design engine. Also, we combine our grading engine with the best design system. So, I mean, you might have a mountainous area. On the photos, we always see that the battery storage systems are placed in straight areas, so you cannot just rotate it. So you have to grade them accordingly. And here we have the pad grading sections. What is the maximum cut height, maximum fill height, slopes, ratios, the biases, everything is here. So we save the engine and then we start placing it. Let's say I want to put some here. Okay, now let's this be my battery storage system. I want to convert it to a BESS area. And some cables are passing over, so I have to recalculate the cables of the solar PV based on this specification. What was this layer? Color code truffle. Let's close this one. Okay, right now I have a BESS area and the cables are routing around it, and I want to place it. So it asks me which type of BESS I want to use. There are 3 popular ones right now in the system, but always you are always free to place them. And you click place, it automatically found it, and it says like this is the rated power and this is the issue, like this is how it should look based on those specifications. This is how I will place it. Do you want me to place it? And our rule engine checks each rule and then puts them, couples them here and places according to the rules. You can see them here. And if you want to go forward, you can also place the PCS kits. You want to set some reserve area because the batteries will degrade over time and you need to add more modules. So you can set some areas as reserve pads. For compliance report, you have to create buildings, lot lines, public ways, or anything combustible. You have to place them around. And you also generate the fire lanes or vegetation clearance just in case something happens. So all those compliance issues are can be selected here. It is a whole detailed section that I will do a much more detailed view. But basically, if you want to draw your BESS using our system, just set the rule engine to its correct version and you are good to go. And right now, let's see, where is it? Let's check the SLD. And as you can see, they are connected to its nearest transformer, inverter, automatically see. We place them near transformer 1 and the system knows that this structure is near transformer 1. So if you go to single line diagram, it will tell you that it is connected to that point. And you can see how it is connected to the grid and the rating have shifted accordingly. All done automatically without you touching anything. Well, here we also have the BOQ section that you can see the details about what have been doing up until now, the power, the number of racks, the modules and everything. You can view it, or we have nice export options here. Again, I don't want to go into too much detail of those, but the first one is the terrain CSV. If you are using PVsyst imports terrain. It is not using for shading analysis mostly, but if you have a very high terraneous areas that the area itself can cast a near field shade to racks, then this data is useful. Earthworks CSV is the one I showed you, just tells you like which coordinate, how much earth you need to move around. This is the first PVcolada 1.5 file. It is the one that is currently you can import into PVsyst. If you want to export this design into PVsyst, then it is this option. And in the future, PVsyst and all other similar software manufacturers will move on to PVcolada 2.0. Basically, PVcolada 2.0 will turn into a file that has your strings, inverters, transformers, your geographical coordinates, the terrain, everything will be in file. So instead of passing the DVG files around, you will be able to pass PVcolada 2.0 files, and you can get a design here, try it in PVsyst or use another software, or any other design you have in another software, you can bring it here. So it will be the future of like saving your power plant. It is the doc format of power plant. It is becoming this one. The design KML is the beautiful Google Earth output. And it helps you to open this design in Google Earth. It ships all the data, like the recs, the other stuff, everything. So you can see the design right here. Let me close the rec labels. And you can see the design here in a very detailed and nice way. This is something you can ship to your clients if you want. Or we have the web section here. Here you publish your drawing to something, and let me show it to you in another view. So it is loading in the background. This is a web-based system where you can just ship your design to any friend with iPhone or anything, and they can easily play around, see it and calculate the shading, or create a video out of it. Here we have the video section. Create videos, etc. And you have the cables export. Here you export each cable, their diameter, from where to where, what is the plus length, what is the minus length, and everything here. Let me show it as well. So here you have the plus length, minus length, total length, cable size, voltage drop, percentage, etc. Or you can export piles. This is especially useful for construction manufacturers because it gives you the pile length of each rack and how many meters are under the ground, how many meters are above the ground. It always turns into a huge file. You see the AutoCAD values, quality check or pre-drilling, etc, etc. You have all the construction readiness here. And also you have the BOQ export. And here you have the total amount of piles, like a pile at this length, you need this amount. Also the civil works, the cut and fill, electrical system, the cables, the sum of the cables. So you can calculate the costs you incur during the project. So the design part is done. And we have done the design part, and we want to go one step further. We want to have an assessment of how our power plant will look. At this point, our competitors go for the yield analysis. Like you ship out the 3D scene and then they calculate the yield and give you any value of like say 10 megawatt hours, 10 gigawatt hours or anything. You end with a value of production. But this is not the case. You cannot just easily ship out a yield work and be done with it. Like this is the design, let's give me the yield analysis. I started using PVsyst in 2008, and when that software first time loaded, I had no idea where to click. Like I just select some modules, the inverters, and I clicked yield. And then one day my boss asked me like, I need a very high yielding power plant in, let's say, Istanbul, I don't recall. And I had no idea about how to run the software because PVsyst is a sophisticated, detailed, hardcore engineering software. It is not for someone to click next and be done with it. And the first thing that came into my mind was like, maybe if I just point the project to somewhere in sub-Saharan desert, then the irradiation will be higher, then we can get a yield value. And I did it, and I shipped this PVsyst output to my boss, and he told me like, are you kidding me? It says, I don't know, somewhere in the Africa, and the modules are 0 degrees, like they are literally looking upwards, but we are in Turkey, like they should be something like 25 to 30 degrees. And I was kind of ashamed, and I started slowly learning the software itself. And during my career as a consultant, I always encountered issues with companies trying to cheat. Like they change soiling, they change incidence angle modifier profile, they change any other, they change the temperature coefficient of solar modules. Because as a consultant, what you do is you believe in the PAN file, you believe in the OND file. Because people ask you to compare, like they ask you to compare JA Solar and Jinko Solar, and they say, which one is producing more? I want to get the more producing more. More or less they are equal. Like they are very, very equal. There are very small differences. But if one company with a new brand claiming that they have more yield and they have just manipulated the PAN file, then what happens? So PVsyst is a great engine. It is bankable, it is proven, and it gives the correct values if, with a very big if the operator is the right, if the operator knows what's going on there and how to do it. And this is the problem in this year about the yield tools. People get some yield analysis, but they don't know how accurate, how reasonable that yield analysis has been done. And this is the thing that we encounter in our company. We just didn't want to ship an assessment software, a yield analysis software, but we want to people to understand what the constraints are and how a power plant should be analyzed. And for that reason, we have created our assessment tool. So here, if you click it, you have the system that asks for the report title, the client, the financial analysis, and the BESS valuation. We have a huge section of what an assessment should be doing. If you are going to use battery storage system, what type of strategy you will use? Like highest price hours, what hours, fixed hours, what is the contracted profile for each hour? Or moving up, if you are charging from clipping, what is the limitation? If you are charging from the grid, what are the lowest price hours? What is the battery's limitations? What is the aging you take into account? They are all filled with sensible defaults, but they are for you to play around. Also, same with the structure of the financials. You can place these financials here. Interesting. Well, actually, we have a default data system here, but for some reason, I don't know, it's not loading, but it automatically populates the area with the defaults based on your project. So you can play around with the values. And then you click your report title, the client name, the report language, or report currency. And it will start running and it will connect to our accredited engineering company, Solarian. So this is not just a tool that you send somewhere and it automatically generates a report and sends you back. It is a sophisticated yield analysis report that is eyeballed by an authority, accredited energy yield analysis authority. So let me show you one report sample because running it is too long. Yeah, here. So this is a sample report we created for a Japanese company. So as you can see, we have a huge analysis of what this system is all about. So skipping the executive part, we first tell you about the project area, satellite view, and we check this area about what the grid is like what power lines we have around them, which power generators like any LNGs or anything, what we have around them. We show it here in the map with a proximity analysis. And we tell you like which transmission line, where is the underground cable, what substation is around, in which direction, what power plants we have around this. So we give you this information about all the power plants that you can see here. See, there are some power plants in those areas. And this is where this project is. And also, moving forward, we also tell you about the water courses, the residential areas, because if you have, let's say, an airport or a residential area, you need to take into account the light analysis, like how many light will be fractured. You have to get this analysis as well. Or if there is a water course, like is there a chance of this water course flooding in? You have to take this into account. So all this data is put into this report. And then you move on to the horizon analysis, like what horizons we have are from two different sources. What irradiation data do we have? And let's compare this irradiation data to available sources, like what does Meteornom say, what does PVcase say, what does NASA say. The problem with the yield software is always trying to get the most correct data out of whatever they are simulating. But we have huge variabilities, like a 2% variability in soiling, and here we have, I don't know, let's check. We have 2.7%, which is a very low value, by the way. This is most of the time is 5% variability between data sources. So we are not trying to impose a yield analysis, and we don't say like this is 10 gigawatts per year, be done with it. We are trying to tell you about what is your uncertainty, like what type of data is going on here. And then soiling losses, like how am I supposed to calculate the soiling losses? 2% is in dry modes. Okay, but now let's move on to a much more detailed one. We have the precipitation values here. Like this is how it will rain. And if I know how it will rain, then from a raining profile, I can generate different soiling values for different months. We also know the DC cables. We have drawn them already. The software knows your losses. So those losses can go directly into this report. You don't need to think about them, or you don't need to use any other values. What should be the losses for our PID, annual degradation, unavailability, albedo? Like what should be the albedo value? Most people don't even know where the albedo section in PVsyst. They just next, but we have an albedo section, and NASA provides this data for us. So why don't we go there and get it for our project site and get a much better reflectivity of the ground? Module thermal losses, transformer losses, everything we have been talking up until now, our losses can come from a system that we can learn somewhere. So why don't we use them? So we have briefly told about our project area, what is near, what are the risks, etc. and what is the data we need to use for analysis. And then we briefly tell about the structure that we have used, what is the best ratio, the clippings. And we want to tell the user like how the overloading in a general sense behaves. Like if I overload 170%, what is my specific yield, like from here to here? So maybe here is better, I don't know. And here are the losses. So up until like 140, we are almost good. We are between 140 to 150, like now we are experiencing some losses. So we first want to give you the idea about how a solar power plant behaves. Like what is the variability of meteorology? What is the variability of DC-AC ratio? What are the losses? What are the gains? Everything. So you read the report and you understand everything slowly. And then we assess the slope. Like we have the terrain, right? We have done cut and fill analysis. We know our slope ratio. So do we have any problematic areas? We know them here. We can assess them. We also know the draining system. We can calculate our draining system's values, like what are the tolerances, how will the water will flow. Let's put it here. Let's let people see it. Let people design according to it. Soil structure. We already know the soil structure. And we have this K value from Russell. So wait a sec, we can calculate the erosion. Is my soil going to erode? Yes, no, it's here, like it tells you. If there's a risk of erosion, you have to know it because you are going to build an important power plant there. It is one of the most important duties of a proper report. So classification of the soil, like what type of soil do we have? What are the values? Like if you ship them to someone that is interested in soil, the application and everything, they know what you are doing. Natural hazards, do we have? No. Climate conditions. What is the snowfall? What is the wettest month? Annual precipitation. And then let's move on to the design. Like, look, it looks great. So what did we use here? What module? What inverter? What is the count? What is the power? And then, like, after mitigating all of those data, we can run a yield analysis. And it has to be done by the professionals. A professional accredited company has to eyeball your design and get back to you with proper values. This is how you handle assessment. This is how you handle yield. You have to go the extra mile. And this is exactly what you see here. And combined with the financial analysis and data system as complementary services, you have this all data here. For example, in this design, simply it does not charge the battery because the system doesn't have any excess energy. So it doesn't work. It tells you like this battery is not running. If you're going to use this one, don't do it. Or you have the financial analysis with the numbers that we have provided. What is the DSCR numbers, minimum, average, year one, what is the IRR, etc. All of them placed here. And most useful graph I love here is this tornado analysis. In the meetings, we talk to people and they just tell us like, if we use this inverter to that inverter, what would be the change? Like the change is roughly 0.0 something. But what if the electricity sale price changes? Now it becomes much more important because a small fluctuation in the electricity sale price has an implication of this much. But a small change of X has an implication of this much. So you get it. Now you understand what you are designing for. You know your constraints, you know the data, you know how it should flow. If you change something around, you know the impact. Changing the inverter or switching to a very similar module of the solar module may not have a great impact on you. But if something else changes meaningfully, you will see it here. And this is how the data should be used. And all the data sources are being used is shown here. Everything is traceable. Nothing is magic. It is pure science here. So what you need to see, it's put here. Well, thank you. It's been 1 hour 40 minutes. It's been a very long walk of the software itself. And I wanted to go over all the features we have, but you know, there are still features that I haven't been able to touch at all. So during your demo or using it, you can try them by yourself. You can ask us questions, because what makes us happy is you being able to design your power plant properly. It is not the software or anything. It is us seeing you achieve your goals, and it is what makes me really happy about what you guys are doing. So if you have any questions, shoot an email, ask our support team to help you with your design. We are here for you. Any questions or anything, just go ahead and ask us. We are here for you to help. I hope you enjoyed it. I still have some water to finish, luckily. And anyone coming to Intersolar next year, let me know, the beer's on me. See you guys. Have a nice day.